Our descriptive statistics tell us what happened. We gathered all this information. This is what we know about it. The idea of inferential statistics is to predict forward. What will happen? What decisions and conclusions, what ideas can I be convinced of with the data I gathered? It is rare that I can ask every single concerned person about a particular topic. More often, I need to ask some small subset. If I ask enough, a large enough subset, or an appropriate enough subset, then I can make decisions. There's a bunch of vocabulary that goes with this idea. A population is the whole group, people, items, whatever it is that I'm concerned about studying, customers, products, routines, whatever it is I want to know about. But it's the whole group. A subset of this is a sample. Ideally, this is a representative group. Now, we'll have to talk about what it means to be representative, but we'll get there. If I'm looking at the whole group, I should have a number, an idea, some sort of answer to my question in the population. We're going to call that a parameter. Some measurable characteristic of the population. As an example, I could look at the American public and ask, what percentage of people between the ages of 18 and 22 drink energy drinks? The entire country, people between the ages of 18 and 22, that's my population. I've defined it. There are a lot of people in that group, yes? But there's a number. I don't know what that number is. But that's something I could measure in the whole group. Almost always when we decide on a parameter, we use a Greek letter. So when I talk about a mean of a population, I'll use the lowercase Greek mu for m, mean. If I talk about a proportion, this is the one that kills me on a regular basis. Proportion should be the letter P. But I want to use a Greek letter. The Greek letter P? No, come on, pi is 3.14. No. If it's a proportion, that's a fraction between 0 and 1. But that's our proportion. The percentage of people that drink energy drinks between the ages of 18 and 24. On the other hand, I can take my sample. I can then measure in that group the same ideas. Then I have a statistic. And correspondingly, these get Roman letters. And that's why for an average, we use that symbol X bar. For a proportion, we'd use the symbol P. My goal is to use my statistic to estimate my parameter. I won't be able to ask every 18 to 22-year-old in the country whether or not they drink energy drinks. I could ask students at Seton Hill who fit that group. I might even not be able to ask all the students at Seton Hill, but maybe I can ask a good number of them. That would be my sample. And then I could say, is this representative of all 18 to 22-year-olds? And does it estimate my parameter in a meaningful way? The idea of this estimation is called statistical inference. I'm not going to get to every 18 to 22-year-old. I'm not necessarily going to get to every 18 to 22-year-old on campus. But there are other reasons to choose samples rather than attempting to ask the entire population. A lot of people in the sample. It's going to be very expensive to ask them all this stuff. It'll give me a more manageable data set. If I were to ask every student in the right age range about their drinking energy drinks, I'd be able to ask, I don't know, 700, 800 people on campus, if I'm lucky. But that's a manageable size data set. I can still get good information from a set that size, provided it is representative. Representative here means that the sample accurately reflects the population. I am pretty sure that more college students pull all-nighters than do non-college students. Make sense? I am pretty sure that I won't have a bias to my results that reflects that in the population unless I take that into account. I'm only asking students at Seton Hill. I didn't ask any non-college students. Uh-oh. Am I accurately going to reflect my population? And if not, how do I fix that? So in order to do this properly, I need to start by defining the population. Who am I studying? What am I studying? How am I going to get my question answered? Then I figure out how I can sample this group. Perhaps what I need to be doing is not just sampling college students, but I also need to sample everybody in Greensburg in that age range, students and non-students, both. Maybe I need to make sure that I take just as many athletes as non-athletes, as many men as women, as many first-year students as senior students. I need to know what my sample should look like to get this. Now, in some cases, I'm not actually asking about people. I'm asking about objects. Crash test statistics. I want to know whether or not the bumper redesign on the car is going to make it safer or not. Well, how do I test that? I got to crash the car, which means every bumper I crash, I destroy. Would be a bad idea to use the whole population, wouldn't it? So I'm going to take a sample and pick some number of cars with the new bumper design, put a bunch of crash test dummies and sensors and other things in the car, have the accident, and see if results are different versus the old bumper. But that means I'm going to do this collection of data for my sample, and then I can calculate some statistics. Perhaps an average, a standard deviation, a variance, a proportion. What fraction of students, what percent of bumpers survived this 5-mile-an-hour crash test? Then I can use these numbers to estimate the parameters. But when I do that, I need to give myself some leeway. I need to say my statistic was 63% of students, people ages 18 to 24, drink energy drinks. But based on the number of people I sampled, based on how representative that sample is compared to the population, I may need to give myself a margin of error. So I will have some sort of confidence interval. For my estimate, some sort of margin of error there. I might actually be testing something. In the question I was just talking about bumpers, I want to know if the redesign made things better or not. Well, there's a question. Can I decide the answer to that question with the information I've got about my statistic and how it reflects on my population? Now that, as part of the estimating procedure, includes performing those statistical tests as the last step. If I want to answer a test question, I need to know how the test works. It may turn out that I don't actually have enough data, or that the data I've gathered doesn't lead me to a clear conclusion. If so, I need to go back up to step 2 and do it again. So this is a cycle, just like at the beginning, we talked about the decision-making cycle. This is the information I have. This is where I can get more information. What changes can I make? Did those changes have a reasonable effect on my business? Now what? I got to close that cycle. Questions? The most common sorts of examples here are things you've seen before. You bought something. I want to know what you think of it. But I sold, I don't know, 10,000 of these items. You think I'm going to get all 10,000 people to respond to an email? Maybe I get 200. Now, I could say, I'm going to look at those 200 responses, take the average of that set of responses from 1 to 10, and I see I get an 8.5 out of 10 for an average. My immediate response is that 8.5 is an estimate for everybody's opinion. All 10,000 people, if I asked them all and I got them all to answer, my average would be around 8.5. Somewhere in there. Then I can start looking at, well, what's the margin of error there? How much leeway should I give myself? So my average X bar is an estimator for the average mu, sample population. Pencil, right? Do you have any idea how many pencils are made in this country a day? You've got the internet in front of you. Somebody tell me roughly how many pencils are made today? Google's a wonderful thing. Should give me an answer for this.
4 million a day in the US.
Holy moly. 5.4 million pencils a day. How many of them are defective? Do you honestly think I can test 5.4 million pencils as they come off the production line every day? Oh, hell no. So let's say I gather from different places in the production line, I take 1,000 and I check those pencils and I determine that out of that 1,000, 20 of them are defective. Now, what's a defect in a pencil? It could be the wood is cracked. It could be the lead is sufficiently off center that it's all the way out on one side. It could be the eraser fell out the minute I picked the pencil up. It could be anything. If these are mechanical pencils, it could be the plastic that feeds the lead, the little lead channel, is sealed closed at one end. The lead doesn't advance properly. The spring is the wrong tension. The eraser falls out the minute I pick it up. But I should be able to say now, based on this sample that I have a proportion of 2%, 20 out of 1,000. If this sample is representative of all pencils, what's 2% of 5.4 million? You have a calculator, a computer, a phone. What's 2% of 5.4 million? Somewhere in this country today, there are 108,000 bad pencils that get thrown out or recycled or chopped up and made into firewood. I have no idea what happens to the bad pencils. So I'm going to assume 2% of all the pencils that roll off of my production facility will be defective in some fashion. If I run a pencil factory, I want to fix this. I'm wasting money, hand over fist. Political polls. The only way you get to ask every single person in this country who they want to be the next president is to have a vote. And every single person who's eligible to vote goes and votes. I need you to look up a statistic for me. What percentage of eligible voters voted in the last presidential election in this country? Right?
65.3%.
So 65% of eligible vote, that means 35% of people who were allowed to or legally entitled to vote stayed home. We didn't get their opinions. But that's 65% of the voting population. That's a really big number. That's 100 million people or so. Then decided. Before the election was held, they did a whole lot of polling. They did a bunch of surveys. They'd call people or send out internet polls or email them or stop them on the streets and ask them in person, who do you want to vote for? Maybe we find that the polls are 58% for candidate A and 42% for candidate B. And then I can infer about the population of all voters. But clearly, the way in which that poll is conducted can affect how accurate of a sample I got. If I want to know how my employees are performing, number of tasks completed per week, in a 3,000 person factory, it doesn't make sense for me to track everybody doing everything. Maybe I follow 50 of them. And then I can infer performance across the factory. Questions? There are a number of challenges in doing this sort of sampling. The way I get my sample could inherently create a bias, in my opinion. As I said earlier, I'm pretty sure that college students drink more energy drinks than non-college students, ages 18 to 22. And so the way I gather my sample could affect this. I want to know the average height of a Seton Hill student. So I go stand outside the McKenna Center and see who walks in. But it happens to be a basketball practice. Think I'm going to get a biased result? I stand outside the cafeteria at noon. Am I going to get a different result? Sure. Am I going to leave people out? Well, sure. Maybe my commuters are only there in the morning, or they're only there in the evening. People who don't go to lunch on campus. Anybody who uses the Cove. All of these options bias my sample. We were talking about elections. A newspaper photo from a number of years ago shows President Harry Truman holding up a newspaper. The newspaper headline says, "Dewey defeats Truman." Harry Truman is holding this paper after being elected president. Why did the newspaper say he was going to lose?
Bias.
Yes, but how did that bias come about? It wasn't deliberate bias. It was sampling bias. The newspaper did a survey. They surveyed people by calling them. Do me a favor. When was Harry Truman elected president?
From the 50s.
Phones were fairly new. So if you had a phone, you could afford a phone. Doesn't that skew your demographic to more wealthy voters? And at the time, more wealthy voters were more likely to vote for the Republican candidate than the Democrat candidate. And John Dewey was the Republican candidate. So the newspaper surveyed all these people by phone, and they all wanted to vote for Dewey. But they didn't ask a representative sample. I also have to take into account the size of my sample. I remember seeing chewing gum advertisements as a young child for sugar-free gum. And it said 4 out of 5 dentists who chew gum recommend chewing sugarless gum. How many dentists do you think they asked? What if they only asked one office and there are 5 people in it and they couldn't find Bob that day, so the other 4 said yes? Is that a big enough sample for you to get any meaningful information? Flip a coin. When I flip this coin, it comes up heads every time. Heads. I'm done. I took a sample. 100% of the time, I got heads. Useful sample? I will actually tell you, though, this does have technically a head on both sides. So I could say it comes up heads every time. There are lots of other potential pitfalls in sampling. I'll go through a lot more of them in the statistics class next semester, but the idea here is that I want to make sure I get a reasonably sized and reasonably representative sample whenever I do this process. Questions? When I do the sample, I draw an inference from my sample to my population. I would like to know if that inference is correct, or if I'm just talking out my butt. So one of the things I need to do is perform some sort of a statistical test. Running that test requires me to have a hypothesis, an assumption, a thing I think is going to be true or false. Formally, I make two hypotheses. The null hypothesis, H0, usually read H null. And it usually means whatever I was testing, there's no effect, or there's no difference, or everything is still the same. If we think about the bumper test, my null hypothesis would be the new bumper is not different than the old bumper. On the other hand, I have an alternative hypothesis. Usually H1, sometimes it's HA for alternative, depending on which textbook you're looking at, which is the opposite of the null hypothesis. Now, I need to be a little anal retentive here. These two must cover every possible outcome, and they must be completely exclusive of each other. Formally, we say that these must be completely exhaustive, exhaust all the options, and they must be mutually exclusive. So if I ask, did the new bumper lower injuries? That's my alternative hypothesis. There was a difference. What's the null hypothesis that goes with that? Not just that they stayed the same. Yes, the new bumper injury stayed the same. They might even have gone up, right? I wanted to know if they got lower. The other options are stayed the same or got bigger. If I just cared about did it change, then I could say were the injuries the same as before? And then my alternate would be they were different. I need to point this out because in the examples listed on the DT100 website that Dr. Burns put up, some of his examples are not completely exhaustive. He does exactly what you did, Ron, and he says if they didn't go down, then they stayed the same, but they might have gone up, and I didn't put that example down. So I wanted to point that out to you. Again, I will be very specific about the way we formulate these null and alternate hypotheses based on what kind of thing we are testing as we move forward. But if my null hypothesis is there's no change here, there's no difference, there's really nothing new here, I need to know, how do I decide which of these is the one I want to say yes to? We're really going to base all of the ideas around just the null hypothesis. And I want to know, should I accept that null hypothesis or should I reject it and thus implicitly accept the alternate hypothesis? How unlikely or likely is it that I get some weird result by chance? We have to decide on a level of significance. Which I will call alpha. Almost always, alpha is set at 5%. So I'm going to run my test. The test is going to give me a number, a probability. Since it's probability, I'm going to call it a p-value. This p-value tells me how likely it is that my null hypothesis happened randomly. For example, my bumpers, right? Did injuries go down? Well, maybe the bumper had nothing to do with injuries going down. The result of my test is the probability that the change in injuries is unrelated to the bumper or is related to the bumper. If it's a very small chance that it's unrelated to the bumper, then I'm going to conclude the bumper had something to do with it. If P is smaller than alpha. So in our case, we're using 5%. If the result of my test is less than 5%, then the evidence does not support my null hypothesis. And I should reject it. So I go and I look at the injuries that come out of this bumper test, and I say, oh, look, based on my information, my p-value is 0.02. That's smaller than 5%. If there was no relationship to the bumper, I would have expected a large p-value. I got a really small p-value. The bumpers must have something to do with it. The only thing I changed in these accidents was the bumper. And it is highly unlikely, there's only a 2% chance, that p-value, that this decrease in injuries happened in spite of the bumpers. So my conclusion is the bumpers caused something. Or at least the bumpers are connected to this decrease in injuries. On the other hand, say I get a big p-value. If I get a big p-value, then the result I got could have happened by random chance. And then I'll go with the null hypothesis that says there's no effect from my bumpers. Now, please understand, there are possible errors we can make. Because I run my test and I make a decision, and either I decide reject the null hypothesis or do not reject. In reality, because I only ran my test, I only tested the sample, I don't know the whole thing. It is possible for my null hypothesis to either be true or false. So let's say I run my test and I decide I'm going to reject the null hypothesis. If I'm here, then I made a good choice. The null hypothesis is false and I rejected it. On the other hand, if I'm here, I rejected it, but I shouldn't have, there's a problem. We're going to call this a type 1 error. It's also referred to as a false positive. Because I decided you should reject, throw it out. If you think of this as a medical test, there's no difference between your medical result and the normal medical result. You're healthy. But I rejected it anyway, you're sick. That's a false positive on the test result, right? I swabbed your nose, you have COVID. But the null hypothesis being true means you don't have COVID. There's no difference. So I made a mistake. The reverse is also true on the bottom line. I don't reject it and it's true, that's good. But if I don't reject it and it's false, you are sick, you do have COVID, and I didn't catch it, what would we say happened on your test? But what kind of an error now? It's not this kind of an error, because your test came back that you were clean, and you're not. So you got a negative test result. I'm not sick, but you are. So we're going to call this a false negative. And that's a type 2 error. Our alpha value is connected to the chance of making this mistake. The smaller alpha is, the less likely I'm going to make this mistake. But the less likely I am to make this mistake, the more likely I am to make this mistake. So there's a trade-off here. And that, by the way, is why most of the time we use alpha being 5%. A large group of statisticians and doctors and other people who rely on these sorts of statistics have decided it's good enough. That's the trade-off between the two errors. The increase in significance, or sorry, the decrease in significance, I need it to be more and more significant, means I need to hold you to a higher and higher standard. Let's think about COVID tests. I'm going to swab your nose. I'm going to check this. If I see a high level of COVID in the sample, you're sick. If I see a lower level, are you sick or not? That's where I have to draw the line, right? How much is required? How significant is the finding in that test tube to tell me whether or not you're sick? If I raise the amount I need to see, it needs to be a whole hell of a lot. Make it really significant, from 5% to 1%. Well, then it's more likely that I'll say, no, you're not sick, even though I saw some COVID in there. It's not enough. And the test isn't sensitive. The trade-off between the two types of errors is important. Now, COVID was a pain in the ass. And a lot of people really decided, oh, we need the sensitivity to be really low so that if anybody's even the slightest bit sick, we don't spread this disease to everybody, right? So they made that alpha value not 0.05, but 0.1 or 0.15. They made it less restrictive. A lot more people got told, you're sick, stay home. Notice that failing to reject doesn't mean that H0 is true or not. It just means our evidence didn't support rejecting it. Remember that our null hypothesis is status quo. Everything's cool. There's no difference, no effect found. But I need to be very particular in the way I write this. We'll talk about that in a minute. Choose your significance level. And our default is 5%. Gather data and calculate your statistics. If I am looking at averages or proportions or standard deviations or variances or something like that, I need to have the numbers from my sample, and I need to have an idea of what I think they are in the population. This is the piece we haven't covered yet. I need to actually calculate a test statistic. And each test statistic has a corresponding p-value. Now, test statistics come in a couple of different flavors, depending on what sort of statistic we are looking at and what we know about our population. The most common ones that we will use are Z's, T's, F, and chi-square. Each of those will have a corresponding p-value. If that p-value is small, smaller than our alpha, then I reject my null hypothesis. And I say there is an effect, a difference, a change. So let's go back to the example we were looking at a little earlier, our customer satisfaction idea. I did a sample. What did I claim the customer satisfaction rating was? Ah, 8.5. So I claim my customer satisfaction has an average of 8.5 out of 10. I'm going to write a claim. My competitors think I'm inflating my numbers. My competitors think I'm lying. They're going to call me out. So my competitor thinks, no, it's lower. And they're going to do their own survey. And they're going to test something. They claim it's lower than 8.5. If they're wrong and there's no difference, the null hypothesis would be, no, I can't show that it's lower. Okay. H0. The null hypothesis is no difference. The alternate hypothesis, the thing I need evidence for, is that it's lower. Sassmore's lying. He's not telling us the truth. It's not 8.5. It's lower than that. Okay, wait a second. Let me write these as mathematical inequalities. I'm going to write an inequality for each of these. And I'm talking about an average. So I'm thinking about the average for my population, that's mu. My alternate is that the average is lower. So I'll write mu is less than 8.5. What's the null hypothesis that accompanies this? I need it to be completely exhaustive and mutually exclusive. So I need the opposite of that statement. Felix? That it's bigger than or equal to 8.5. A technical note here. Because I am asking about one direction in this inequality here in my alternate hypothesis, this is a one tail test. So the test I am going to do is called a one-tailed test. And the reason it's one tail is because this inequality is only to the left. It is less than 8.5. If I said it was 8.5 and they said, no, it's different, how would I change my hypotheses to reflect that? Yes, sir.
Zero.
And if it's higher or lower, I can just say it isn't 8.5, right? Now notice, it could be lower or higher, yes? That gives me two directions I could go. If I were to do this same kind of thing I just was talking about, now here I'm doing a two-tail test. Because I have two different directions. I could either be lower than or higher than. Now, depending on the type of information I have, I'm either going to do, for the testing I'm doing, I'm either going to do a t-test or a z-test. Most of the time, I don't have enough information to do a z-test. So I end up doing a t-test. Advantage. I don't have to do this manually. Once I've gathered my data, all of this will be run through Excel. Lots of different programming languages have t-test availability. I'm only gathering information about one item, one sample. So in spite of the fact that I have one tail or two tail, these are one sample t-test. I'm only asking about one piece of information, customer satisfaction. What's your rating? Once I have done this, what this test does is it looks at a new function, a probability distribution. It's called the t-distribution. And we are able to examine how likely or unlikely this rating was to happen randomly. It is possible, instead of a one sample, you do two samples. I could ask did this product make your life better? You were using it before, you were using it after. You decided to take a particular medication. Did your symptoms go away? Yes or no? Well, then I'd have a before and after sort of comparison. That's two samples. Sometimes it's the same person both times, in which case we call it a paired sample. Sometimes it's not. Half of you are going to take a remedial statistics course in person, and half of you are going to take it online, and I'm going to compare the two groups. The same person didn't do both things, so they're unpaired. We don't usually call them unpaired, we call them independent. So I run this test. I get a p-value. What do I do with that p-value? So you compare it to the alpha. Okay. Once I compare to my alpha, let's suppose there are two options here. Either P is less than alpha or P is not less than alpha. Let's suppose we're in the first one. P is less than alpha. What do I do? Felix. Reject what?
True that it's
There's something specific I need to reject or not reject. We're talking about my customer approval ratings.
okay. In this case, we reject the null.
Exactly. I reject my null hypothesis. I accept the alternative. And that means in this case, depending on which version I'm doing, my null hypothesis was, in the first version, it was that my average is bigger than or equal to 8.5. In the second one, it was my average is equal to 8.5. So if my p-value is really small, I say no, that is not the correct statement. My p-value is smaller in the first case, or is different from 8.5 in the second case. Here, if my p-value is large, I don't reject. So maybe I run my test and I say, oh, the p-value is 0.13. With a p-value of 0.13, I'm not able to reject the null hypothesis. My competitor who did the survey is unable to demonstrate that my customer rating isn't 8.5. It's he doesn't have evidence to say, no, you were wrong. So that's the necessary part for having two hypotheses. The alternative hypothesis is the one that needs the evidence. If I'm trying to show something, that's the thing I want to be my alternate hypothesis. Caffeine consumption before exercise increases muscle growth and vascular health. That's a claim, right? I've seen all these pre-workout jugs that have 300 milligrams of caffeine per dose that you take before your workout. By the way, 300 milligrams of caffeine is 2 to 2.5 standard cups of coffee. It's an entire 6-pack of Mountain Dew. It's a lot of caffeine. Does it increase oxygen stats during workout? Does it increase muscle growth? Does it increase blood flow? I can run actual tests. Go over to Dr. L's lab over in Lynch Hall in Boyle and get on the treadmill after you take your pre-workout, wait however long, and we can put a blood oxygen monitor on your fingertip. We can start you on the treadmill and we see if your oxygen stats go up. And we can do the same thing without you having the caffeine, right? 2 separate days, 2 different behaviors. That's a test. If I'm trying to show it does, that's what I want to be my alternate hypothesis. My null hypothesis is there's no difference. There's no effect. If I have a new version of a product, I did this product revision. Does the new version sell better than the old version? My classic example of this is the unmitigated disaster of the 1980s called New Coke. You go down and buy a Coke, it says Coca-Cola Classic. Do you know why it says Classic on it? Because in the 1980s, they tried to change it and everybody hated it. So they brought back the old formula and changed the name. So I go and I say, all right, my old version sold, of whatever product I'm dealing with, sold 1,000 units a month. New version, does it sell better? That's the question I want to answer. So I'm going to again ask about an average. Are my average sales better than they used to be? I need a null hypothesis. I need an alternate hypothesis.
Would the null hypothesis be either it sells less than or equal to 1,000?
That my new average sales are less than or equal to 1,000, then my alternate hypothesis will be that my average sales are greater than 1,000. Please notice, I changed the direction. The alternate hypothesis now is greater than 1,000. This is a right tail test. So now what I'll do is I'll gather the sales data for the next year, and I'll compute the average over the next 12 months, and I'll figure out, did we get a different average? Is it bigger? Is it smaller? And I'll get a p-value. Again, I'm only looking at one sample, sales numbers. So this is a one sample t-test. Only have 12 data points. Small number of data points, t-test. Less information. If I then get the p-value hey, the p-value is 0.02. What does that mean? Yes, my p-value is 2%. But what does having a p-value of 0.02 tell me? I'm back in my decision-making position, right? Felix? I'm going to reject the null hypothesis. The smaller the p-value is, my assumption is that the sensitivity here is 5%. You just told me the 2%, right? 2% is smaller. If it's smaller, my null hypothesis is rejected. I have an extraordinary amount of evidence that leads me to believe the new product sells better. My sales should be averaging more than 1,000. I don't have a data set at the moment, but let's do one more example. I make compact fluorescent light bulbs. One of the ingredients in compact fluorescent bulbs to make them fluoresce, including the bulbs above your head, which aren't compact, is mercury. There's just one problem with mercury. Anybody know what the problem is with mercury? Mercury is poisonous. The Mad Hatter in Alice in Wonderland is mad because the way you make felt used to involve mercury. And to make a hat, you had to do all this cleaning. You needed mercury. The Mad Hatter went bonkers because he was exposed to mercury. But modern CFL bulbs advertise how little mercury they contain. So a company claims bulbs contain less than 3.5 milligrams of mercury per bulb. Along comes the EPA. They gather up 24 bulbs and they start to test them. I need a null hypothesis. I need an alternate hypothesis. If the company is trying to prove the bulbs contain less than 3.5 milligrams of mercury, that should be my alternate hypothesis. If the EPA is trying to prove, no, your bulbs contain more, that should be my alternate hypothesis. So who's doing this test? That changes the way you phrase the hypothesis. What are you trying to prove? Because the thing you're trying to prove should be your alternate hypothesis. We'll go through more of the actual calculations and doing the tests on Tuesday. You are reminded that you have the 2 quizzes for Module 2 due on Tuesday. I will see you all then. Have a wonderful weekend.